geometric proofs, but instead of relying on our geometry theorems that we know, we're going to use vectors to prove some of these geometric proofs. But things to keep in mind when you are playing with vectors. In your picture, because it's not necessarily going to be on a coordinate plane, because we're talking about geometry here. So we choose a vertex or some other key points in the picture to represent the origin. So where all of those vectors, the position vectors, are coming from. Remember that the sum, or difference, depending on what you're looking at, of vectors will create a triangle. Parallel vectors, we know they're multiples of each other. The angle between vectors, we can use the dot product to find that. Perpendicular vectors, indeed, have a dot product that's equal to 0. That could be useful. And if I want to know what the vector is, I know it's always going to be, well, head minus tail. That's how I know what the vector is representing. Let's do this then. We're going to prove the diagonals of a rhombus are perpendicular. Here's my rhombus. Conveniently, I label one of the vertices O, so I'll use that as the origin. Every vector that's coming from O, I'm going to give it a name. So I'm going to say OA, I'll just call it A, and OC, I'll call it C. Now the diagonals, that's what we're trying to prove are perpendicular, so it makes sense to come up with an expression for those. So OB would be A plus C, and AC, head minus tail, would be C minus A. I suppose I could have made it the vector CA if I wanted to, but then it would be A minus C. It doesn't really matter. Perpendicular, well, the dot product, that's useful for showing things are perpendicular. So let's have a look at those two vectors when we find the dot product. And what we've got there, although the first one's written the other way around to what we're normally seeing, but we've actually got the difference of two squares there. So C dot C, which is the magnitude of C squared, minus A dot A, which is the magnitude of A squared. But hang on, this is a rhombus. So we still use some geometry, but I know the magnitude of that vector A is the same as the magnitude of the vector C because sides in a rhombus I know are equal. Well, therefore that's got to be 0. Dot product is 0, they're going to be perpendicular to each other. What a good old Pythagoras' theorem. There are so many different ways of proving Pythagoras' theorem. Here's a right angled triangle. In this case I've made the right angle O. So I'll call OA the vector A, OB the vector B. Pythagoras' theorem, of course we know what that is, it's all to do with the hypotenuse. Let's get an expression for that. So the vector AB would be head minus tail, B minus A. Right? Pythagoras' theorem is what I want to prove. So OA squared plus OB squared. Now it's not the vector squared, but the magnitude of that vector squared. So the magnitude of A squared plus the magnitude of B squared. Now, AB squared, I want to show these things are equal. Well, that's going to be the magnitude of B minus A squared. Well, that's B minus A dot B minus A, which is B dot B minus 2A dot B plus A dot A. But hang on a sec, I know that OA is perpendicular to OB, so therefore this A dot B must be 0. Well, that means AB squared is B dot B plus A dot A. Well, let's go back to the other one. Well, that is the same, isn't it? Because B dot B is the magnitude of B squared, and A dot A is the magnitude of A squared. So indeed, those two things are equal, and we've proven Pythagoras' theorem. Ooh, this one's a little bit more interesting. ABCD, quadrilateral. PQRS, midpoints of those different lines. What type of quadrilateral will PRQS be? Wow, so what to do? I'm going to choose A to be the origin, that's the one. So all of those vectors that are coming out from A, I'll give them a name. So AB I'll call U, AC I'll call V, AD I'll call W. There's my vectors. Now we need to find out some information about P, Q, R and S because that's the shape I want to prove. So let's have a look at it all. Well, remember these points are the midpoints. So I know AP would be half of the vector AC, and AC is what we called V, so it's a half V. I've got an expression for that. I could do the same with the other ones. Well, BQ, that would be a half of BD. Now I haven't given BD a name yet, but BD, head minus tail, would be W minus U. So it's those vectors. AR, half of AD, we gave that a name, so that's a half of W. BS, that's a half of BC. Again, we haven't got a name for that one yet. So head minus tail, that one would be V minus U. We now have the four sides of this quadrilateral that we want to play with. See, I'm going to look at PR. How could I get PR? Well, I could get PA and add AR, because if I smash that together, the A's disappear, and I've got PR. So I add those two together. Now, SQ, I can do the same sort of thing. Hang on, they're the same vector. They both turned out to be a half of W minus V. So they are equal vectors. But now if we're talking about the shape that it forms, it must be a parallelogram then. Because in that shape, the opposite sides are equal vectors. And what do we know about equal vectors? Their magnitude's the same, so the length of those sides are the same, and the direction that they go in will be the same, i.e. they're parallel. A pair of opposite sides that are both equal and parallel, got to be a parallelogram. Let's have a look at an HSC one. So this one from 3 years ago now. We've got a trapezium, ABCD. BC is parallel to AD, and the length of those diagonals are equal. They've already told us what to name these. So AB is going to be A, BC is going to be B, AD is equal to some constant times BC, and it's a positive constant. We have to show this wonderful expression. Let's get some information that I might be able to use. Now, AC, I'm going to start with A being my origin, if you like. So I'm going to get names for things coming out of there. I know AB is A. AC would be AB plus BC, so that's A plus B. Actually, I'm going to get a name for BD as well. Kind of made sense, actually, because that's the information I've been given, that those two things are equal. So let's get expressions for AC and BD. Now BD, head minus tail, or another way of thinking about it is getting BA and AD, smash them together. But it would be minus A, because it's going in the opposite direction, plus some constant times B, because BC is... We've been told the magnitude of these two things are the same, but the magnitude squared is the same as saying the vector dotted by itself. So I know these two things. This I can now, for want of a better word, expand out. I'll get A dot A, which I know is the magnitude of A squared, 2A dot B plus B dot B, which is the magnitude of B squared, and then over on the other side I get, well, that expression there. Okay, I'm trying to end up with this 2A dot B and so on is equal to 0. Right, let's play around with it. Well, it makes sense to move everything to one side because then I've got equals 0 on the right hand side. No, that's what I want. Let's play with the left hand side. 2k plus 1a dot b, 1 minus k squared, magnitude of b squared. Not quite what we want, but I notice 1 minus k squared. That of course is the difference of two squares. We now have a common factor of 1 plus k, but we know k is a positive number. There's no way that k plus 1 is equal to 0. Therefore, it's perfectly fine for me to divide by k plus 1, and it would be valid. The only thing we're not allowed to divide by is 0. We know k plus 1 cannot equal 0. So in my working, I make that point because the question is, hang on a sec, where did k plus 1 go? How did it magically disappear? Why are you allowed to do this? So you explain yourself. If it's not immediately obvious, write an explanation for what you did to make it obvious. And that is the expression that they wanted. So we got it. Okay, what about the next year? 3 different points on a circle. The centre of the circle is O, and well, they've named all the vectors that are coming out from O. So OA is A, OB is B, OC is C, and H, this little vector here, is going to be A plus B plus C. Oh yeah, I could see that. If you imagine moving those vectors, A, slide the B up, add in the C, we end up down here. Show that BH, which isn't drawn in for us, but if we were to draw in BH, and then it would meet CA, but they would be perpendicular. Perpendicular, dot product. Okay, let's see what happens. Well, BH, haven't got an expression for that, have I? Head minus tail. H minus B. I've now got an expression for BH. CA, same deal. Head minus tail, I'll get A minus C. So BH dot CA, I want this to be 0. That's what we need it to be to show that these things are perpendicular. So, but H minus B is also, let's go back to our diagram, H minus B, another way. So what was it? We were told H is equal to A plus B plus C. If I play around with that, I can say, well then H minus B must have been A plus C. Just rearranging that expression they gave us. Oh, thank you. Difference of two squares, A dot A, which is magnitude of A squared, and C dot C, magnitude of C squared. But, hang on a sec, they're radii of that circle. They're going to be equal in length. Therefore that's 0. They're perpendicular. The dot product is 0. So a couple of these little nice geometry problems to play with.